Look, I'm just a geologist. I like rocks. I love rocks.
Hello, everybody, and welcome to the Geology Flannelcast. My name is Steve.
Hey there, everybody. This is Chris.
Salutations. I'm Jesse.
Oh, look at Jesse not having the awkward silence today. It's
Yeah.
like he's on his A game today.
I'm all self-conscious now because I was like, don't forget I have to podcast tonight. I was like, hello, everybody. Welcome to the Geology Flannelcast. I was like, come on, man. That's going to be in my head.
Yeah, she's playing mind games with you.
She is. She's like, yeah, sometimes me and the kids listen from upstairs. Like, oh, they started. Man. Oh.
Well,
Anyway.
Hello, everyone. Thanks for joining in today to the Geology Flannelcast, the premier geology podcast. Hope everyone's doing all right today, having a good day. We got an episode that is about 400 million years in the making today. No, more than that.
More than that. Come on, man. About a bill.
Yeah, full bill. I like that. Today is we're covering the Appalachian Mountains today, right? And it's a topic that it was actually episode number 2 way back in 2014, right?
Yes.
You get the date handy, Steve?
I do.
It was a long time ago. We did the
date handy.
This is a topic that I'm stalling right now. This is
it was January 2014, January 30th, 2014.
January 30th, 2014. My goodness. This is a topic that all three of us are, really into. We've basically been studying this topic for years, and we decided that it kind of needs what do you guys want to say? Not a reboot, like a kick in the butt, or I don't know.
I'm just dusting it off.
Yeah.
Kicking the tires.
Dusting it off. Yeah.
Just want to make sure you don't forget about them.
No.
So
these rocks are literally in my backyard.
Yeah. This is so we figured we jump back on this topic, try to hit some new things that actually we just recently learned. And the funny thing about this is each of us have been studying the formation of the Appalachian Mountains for 10 plus years. I'd say there's at least 30 years of studying of the Appalachian Mountains between the three of us.
Now
Maybe
you're putting a lot of pressure on us.
Mm-hmm.
No, but would you let me finish? But this is a topic that we were just talking about this before we started the podcast. The more you study this, the dumber you feel.
Okay. Yeah.
Is that better now, Jesse?
That's in some ways the Appalachians are my white whale. I'm chasing them, but will I ever truly catch them, or will they kill me first?
They'll probably kill you first.
Yeah.
I don't know.
We're all doomed.
But no, we've all done work in the Appalachians, done some research work and stuff. And I don't know, it's we're all East Coasters here at the Geology Flannelcast. So it's a mountain range that's near and dear to our hearts. And so we decided we'd give this a little nudge. How about that?
Yeah. So it ranges from Canada all the way down to Georgia. I guess maybe further south.
Yeah, Georgia, a little bit of Alabama.
Yeah.
Alabama.
Yeah, but
yeah. Some would say they're the original and the best.
The OG mountains.
Yeah.
So this is a topic that's, oh my goodness, like geologists have been studying this for a really, really long time. Since, what would you say, maybe since the 1800s or so? I mean,
yeah, I isn't this where, like, before plate tectonics, the idea was geosynclines, which is where to explain sort of mountains, which is a weird building up of sediments causing the crust to deform and sort of bulge. And I want to say a lot of it was by looking at the Appalachian Mountains. It was conceived by early geologists in the mid 1800s looking at the Appalachian Mountains. They are the classic mountain range.
That's really interesting. You said that because
Thanks.
just throwing you a bone there.
I appreciate it. All right, I'm going to sign off.
All right, that's it. Jesse's dropping his bike right now and walking out the door. I always like telling that whenever we talk about like the previous, theories on how mountains formed before plate tectonics, which is kind of crazy. We've known, obviously we know about mountains, we've seen mountains, but we really truly didn't understand how they formed until plate tectonics came about in the 1960s, and it's so I always find that like super fascinating that we just didn't even know the basics on how mountains formed. There's another form. So one of the I should say this, one of the previously before plate tectonics, as Jesse was talking about, was people thought mountains formed through this geosyncline theory, but there was another theory. I think I might have talked about this briefly on the podcast about how mountains formed that had to do with the Earth cooling down. And the theory goes that it was kind of like the Earth started off as hot, and as it gets older, it starts cooling down. And as it starts cooling down, it starts to like develop these like ridges, almost like a grape turning into a raisin. And obviously that's not how it works. So, but
What?
So
it's obviously catastrophism or Neptunism.
Yeah.
The Neptunism, everything came from the Great Ocean.
Exactly. Yeah.
Everything precipitated. And what was it? Werner von Gottlieb, right? The head, the most outspoken Neptunist.
Yeah.
Yeah.
Sometimes you don't need to be the smartest man in the room, just the loudest.
That was a good pool there with that name.
But I mean, back to Jesse's point of the Appalachian Mountains being like the OG, like people studying this, on the other side of the ocean, that's where, our boys, William Stratus Smith and some of these other guys were, it's essentially the other side of the zipper, if you will, of the Appalachian Mountains.
Yeah. So it extends the Appalachian Mountains, or they obviously on the other side of the Atlantic, they don't call them the Appalachian Mountains, but it's part of the same chain, going up in Scotland and then up through Scandinavia.
Caledonia up in Scotland and parts of Snowdonia and Wales. And even on Africa, you have the Atlas Mountains.
Mm-hmm.
I think the Little Atlas and the Anti-Atlas, which are great names for mountains. Like I like when you put those little ways to describe them.
The modifiers.
Modifiers, yeah. The Anti-Atlas, the evil Bizarro Atlas.
Yeah, right? Like I feel like there should be a gateway to hell there or something.
Well, so we're getting a little bit ahead of ourselves. We're already destroying the Appalachian Mountains and dissecting them and cutting them up. And let's how about we start off in the beginning?
In the beginning.
The first thing that says excuse me. The first thing that says on our outline is, this is literally what we're going off of, ladies and gentlemen. Mountains go up, mountains come down, the end.
And there's nothing more you need to know about mountain building.
Well, thank you, ladies and gentlemen. Thank you, Formatting Formula, for listening, and we'll see you next week.
So the Appalachian Mountains, I guess, to kind of start things off, is obviously, I guess you could say there's three major mountain building events that occurred that are recorded in the Appalachian Mountains, but really there's kind of a fourth one. All right. And this fourth one is the oldest one. All right. And I guess we'll just kind of touch on this. I guess that's the point. And then kind of go from there. But like we kind of said earlier in the podcast, everything starts off about 1 billion years ago. All right. We had there was a mountain building event called the Grenville Orogeny. Right. So when we say this term orogeny, that's just like basically like fancy geologic speak for mountain building event. So got to talk about the Grenville first, because this actually is part of the Grenville Mountains are incorporated into the Appalachians that we know of today. So Grenville, this is back in Precambrian time. We're dealing with like about 1250 to 980 million years ago. All right.
Can I jump in here?
Yeah, go ahead.
So I just want to make a note about this time period. So this is all Proterozoic, so a billion years ago. The last period in this Proterozoic with the Grenville, so right around a billion years ago, is called the Tonian Period. And the Tonian Period's interesting because it's one of the periods where we get our first really definitive fossils of animal fossils. So like
it's like complex organisms.
Yeah, like what you would call a metazoan, I guess, or so not like, and this ties in with our life episode, that's why I wanted to mention it, where we talk about we see early life, cyanobacteria, other bacteria, single-celled organisms. This, we get our first sort of definitive, this is an animal, Atavia antiqua, which is a type of sponge. We're not going to get too crazy. We're still simple life. But
no backbones, no vertebrae yet.
No
vertebrae. We're not even close to that yet.
Let's
everything's still living underwater too. Like,
right, but the soft parts are becoming harder.
Yeah. And the Tonian actually stretches. That'll make
across.
I'm gonna loop back on that. Stretches from about 1 billion to 720 million years. So it's like 300 million years of time. And it ends with one of my favorite periods, Snowball Earth, the Cryogean.
Good old Snowball Earth. We've never done an episode on Snowball Earth.
No, we should. Also, Tonian comes from the Greek tonos, which means stretch.
Nice. I like how
I'm full of fun facts. And this is also a period. Let's just make this a Grenville episode. This is also part of a period that's sometimes called the boring billion. And it's supposedly this time where like there's not much happening, but that's not true. There's an orogeny.
Right.
There's the first definitive animal.
I want to line up those scientists and smack them.
Yeah, it needs to check themselves.
Yeah, come on, man.
I know it's a sponge, but it's an exciting sponge. It's
like the first one.
Yeah.
The first sponge. Yeah.
Yeah, they had little square pants.
Yeah, in my mind, I'm picturing
under
like
the sea.
A cyanobacteria who's just like, I'm gonna be better than this, like squeezing really hard, and then poof, turns into a sponge. I don't know how evolution works.
I was referring to SpongeBob, but
yeah.
I think what Jesse's referring to is punctuated evolution, maybe.
Yes.
If you think about it,
I wish I can.
Yeah. Yeah, let's see. Visualize what you want.
There you go.
You want to be a sponge?
That cyanobacteria set up a vision board. Had some meetings with friends, figured it out.
So anyway, it's an interesting time period, but mainly because we're starting with the Grenville orogeny.
So the Grenville orogeny, like it happened a little bit west of where the Appalachians are today. I forget what we're doing with like around like Arkansas-ish, right? Or the Ozarks, is that correct? Off the top of my head.
Yeah, and I include it with this because it trends north to south where you find the Appalachians today. You have the similar sort of trend of the Grenville up through Canada.
So yeah, so the got to start off with the Grenville initially, all right, and so that happens, and Precambrian time ends, right?
So that happens.
So we're gonna fast forward about 500 million years now.
Yeah.
So talk about the boring billion. This is kind of like the, I don't know, $500 million that we're not even going to talk about.
Yeah, you have snowball
like,
Earth, the radiation of all multicellular life, development of all phyla. Anyway, here we are in the Ordovician.
This is like one of your favorite time periods, right?
It is. It's up there. Do you know what my favorite period is?
The Cryogenian?
No, it's one of them.
I don't know. I feel like this answer changes every week.
Probably does. But no, this is a way I'm going to work in a through line for all our episodes here. It's got to be the Carboniferous.
I was going to
Pennsylvania.
Once you said,
Come on. Come on.
It's quickly turning into one of my least favorite periods. Just to balance it out, the yin and the yang on this podcast.
No, I've got a good project we should work on there. So,
all right.
Mine's the Anthropocene.
Like right now?
Yeah.
The period that's not officially recognized. It's going on right now as we speak.
Yeah.
I guess it wouldn't be a period, it'd be like an epic.
Epic? I don't know. Steve's gonna go turn on.
No, it'd be a period.
They're
gonna go out and turn on his car. I'm gonna make this period happen.
Yeah, I guess maybe it would be an epic or an age. It depends on who's defining it. Yeah. Anyway, sorry, we're digressing too much.
Yeah.
Too much, which is odd.
Yeah, right. I think they're trying to make it an epic.
An epic. All right. All right. So the first round of mountain building events on the east coast of modern day North America. So this continent wasn't known as North America for what we're dealing with. Should we call it North America for the podcast to keep it simple, or do you want to call it Laurentia?
Let's call
yeah,
it.
I mean, yeah. So Taconic, or the Grenville came together to create Rodinia, right?
Oh, we didn't say that. Yeah.
So, one of the first major supercontinents, Rodinia, and then that 500 million that Chris wants to skip, that Jesse imparted all that knowledge of, like basically all life as we know it started. That's essentially when it's ripping apart.
Yeah, it breaks up.
It's not only is it ripping apart, it's ripping apart and then it's starting to come back together. And then once it comes back together, that's when we have the Taconic. So
not quite. Yeah, well, yeah, when it's starting to come back together.
Yes, when it's starting to come back together.
Like one of the first waves.
Yeah.
This what ends up happening, what Steve's getting at, you get into the volcanoes, Steve?
No, yeah. I mean, I just wanted to, like you were saying, do we call it North America or do we call it I think we can call it North America
if you want to call
clarify.
it North America, call it North America.
All right.
I just want to mention, like, at this time, when you're thinking about what things look like and where things are, you have to keep in mind that North America is less than half the size it is now, and we're in the southern hemisphere, down near the South Pole. Like, visualize
everything's all rotated around. Yeah,
visualizers. We're basically Australia.
Yeah,
is what I'm getting at.
On as far as where we are on the planet. Yes.
Yeah, and maybe I wonder size. That'd be an interesting little thought experiment. What would our size be?
I mean, it's obviously smaller. Like, you wouldn't have California or anything like that. I believe where the western boundary of North America at this point probably would have been somewhere around Utah.
That's what I would say, Utah.
Yeah,
Colorado, somewhere.
Yeah, before the Laramide, but we're not even going to get to that.
There's no New Jersey, no Florida. No comment.
So, and there's not even an Atlantic Ocean. The ocean that is just east of the proto North American continent. Well, it's called Laurentia, right? But we'll just keep it simple. North America. What the beginnings of North America?
Proto North America. It's the ocean that would be adjacent to the modern day east coast of North America. It's called the Iapetus Ocean. We've actually talked about the Iapetus Ocean on the podcast before.
So Iapetus, let's see if I get this right. It's on the outline. Iapetus is the father of Atlas. Is that what we said in the Atlantic Ocean is named after Atlas, and Iapetus is the father of Atlas.
Yeah, but what's he the son of?
Well, there you go. I'm just learning this right now. Gaia and Uranus.
So Uranus.
Are we saying Uranus?
I don't know.
Every
so
time
Uranus, I'm just so used to saying it in class. Uranus is the god of the sky, and Gaia is the god of the earth.
Right.
And their son, Iapetus, is the water.
Was Iapetus a Titan?
Yes.
Did Gaia gave birth to the Titans, right?
Gave birth to the Titans. Yep.
All right.
Yeah, a bunch of them.
Yeah. There's actually I was watching. There's on Amazon. There's Amazon Prime. There's a story about Greek mythology, and I was watching about the. It's actually kind of strange about the
whole
Titans.
family. You look at that family tree. Ooh, that would not fly today.
There's there are some issues with that, and I think that the Titans. Let's see. Obviously, Uranus was the father, and Gaia was the mother, and the Titans were stuck inside Gaia, and she couldn't like birth them, and it was a whole thing, and it gets very graphic, and I'll leave it at that. But why are we talking about this? Moving on.
Exactly.
So just off of what would be the modern day East Coast of North America, it was really different than what it is today, right? We had volcanoes. There was we'll call a volcanic island arc chain just off what's the modern day East Coast of North America.
So what are we talking, like Japan?
You can kind of think of something like Japan, or obviously we're not going to know the exact shape of what this island arc looks like. We see the evidence, we see the volcanic evidence of this stuff in the rock record. There's ash deposits that you can see. I've touched them with my own hands.
I have too.
I've seen the bentonite. The ash turns into.
Have I? I assume I have.
Yes.
Where?
I saw mine in Virginia.
I've been to Virginia. Let's just assume I have.
A lot of the those Ordovician limestones.
Yep.
You can see little bentonite. It's very subtle. But you can see little bentonite stringers in the Ordovician limestones, and that's actually just volcanic ash.
Have I touched? No, I guess Devonian bentonites. I've messed around with in PA.
Yeah, we've definitely seen Devonian ash deposits, but it's just funny. Have I touched? No.
Well, I'm going to put that on the old summer bucket list.
Touch some Taconic bentonite.
There's where is it? Out in Stanton, Virginia is about where I saw where these. It doesn't matter.
It does not matter.
It's right next to a Burger King. All right.
Yes.
Ooh. All right. Now you're selling me.
Yeah, right off the highway. Right off of I-81 right there in Virginia.
It's a good road.
Very good road.
I like to throw those little one-liners in to really throw you off your thought. Okay.
So we had these volcanoes, right? And then in between North America and these volcanoes, there was a bit of oceanic crust, right? And so we have subduction associated with this. All right. We have these the subduction zone, which obviously is fueling the island arc. So as Steve pointed out, you could kind of think of it something like Japan, or Indonesia, or just a chain of volcanic islands just hanging off the coast there.
Chilling.
The thing that got me with this is, like, if you're picturing, even if you picture just modern North America, and you think of like the Atlantic Ocean today, if you would think of subduction starting, you're going to imagine subduction occurring under North America. But in this case, the way the microplates were, there was two microplates, basically oceanic plates, to the east of us.
Yeah.
And so subduction starts to the east.
Mm-hmm.
And that's where the island arc forms. And, I always got confused with that when I think of like this island arc, the Taconic island arc forming. I always just assume, I don't know, it's just the way I visualize it, is subduction occurring towards the continent. But in this case, it would be away from the continent.
Yeah, because you're getting that little sliver, that little bit of oceanic crust between North America and the volcanoes. That's getting pushed down.
I like how you call it the volcanoes, like it's like Skull Island or something.
All right, the island arc. All right,
the volcanoes.
Beware of the volcanoes. You find ghost ships there.
We were talking about ghost ships before the podcast started.
Do you think we digressed already? Whew.
Yeah.
Let's not go down the ghost ship path.
Okay. So what's happening now is this little bit, this bit of oceanic crust between North America and the volcanoes, also known as the island arc. It's getting subducted, and North America is getting closer and closer to the island arc. And then all of a sudden, whammo, boom, that island arc gets sutured onto North America. This is called, ladies and gentlemen, the Taconic Orogeny.
Yeah, just think of it as like it's a car accident happening in slow motion, and eventually it just smashes in and gets stuck to us.
And again, I'm emphasizing this point here. The island arc and the continent, you would imagine the smaller of the two, the island arc, moving towards the continent. I mean, I guess they're moving relative because everything's moving. But in this case, because of the way subduction is working, the continent is moving towards the island arc. Getting smashed.
Continent's like, get over here. You're mine.
No, the island arc is like, get over here.
Unless the continent's, you can think the continent chasing after the island arc.
Yeah. Oh, yes, I get where you're going. Yeah, I was picturing it like a Mortal Kombat fatality.
Well, when I said get over here, that's like straight up 1990s Mortal Kombat. Yeah.
I
make only topical references, but we are talking about 480 million-year-old rocks.
Yeah. So the island arc system gets sutured onto North America. The two of them collide. North America catches up to the island arc, or the island arc pulls over North America. However you want to look at it, right? So the volcanoes slam onto North America, and like I said, this is the Taconic Orogeny, right? This lasted for 40 million years. This is kind of a crazy amount of time. Like when you think about it, 40 million years. So you just got this like shoving and this pushing of the island arcs, suturing onto North America. So this is between 480 and 440 million years ago. So that happens. That's like the first wave. And I was looking, this isn't on the outline here, but I was reading some going off script, baby. I was reading some stuff about what were like the heights of the Taconic Mountains when they were like baby mountains, and we're looking at like 20,000 feet or so. So that's like equivalent to like actually the Andes. 20,000 feet is bigger than any mountain right now in North America. Mount Whitney's I guess if you want to go, I'm sorry, I made a mistake there.
Contiguous.
The contiguous. Yeah. Mount Whitney would be the in California, would be right now 14,000 and change. But yeah, Denali is, I just thought of that. Denali up in Alaska is,
I mean,
20.
It's only 20 only.
Oh, no, 20.
Do you know Denali? Is Denali the one that has, it's like super technical to climb, right? Because from base to summit, it's higher. It's a greater elevation gain than say Everest.
You know what? I don't know off the top of my head. I do know that Denali was a pain in the butt to climb. I had a buddy that climbed it, and it's a true story. They got up to the top. So they had all these he went with like a guiding service, right? got to the top, and they had they had all these parkas and stuff because they thought the weather could have been like horrendous. Get to the top, and it was like 50 degrees or something like that. It was like incredibly warm, and the guide goes, "Hey fellas, we're going to take the summit picture. Put those parkas on because nobody's going to believe you're at the top of Denali right now if you're not wearing these like heavy duty parkas."
That's funny.
That's ridiculous.
But yeah, apparently he summited. It was like crystal clear conditions and like, yeah, super nice. But anyways, so that's about the height of the Taconics when they were baby mountains. So the Taconics eventually start to erode and they start to break down, and they're not around anymore. So
what is the Cameron's line?
So yeah, this was something that I had never heard of until I started looking into it.
Yeah, I've never heard of it either. I see it on the outline.
Apparently it's just you can still see in a lot of these rocks or in the structure, the geologic structure is still present, the suture zone. It's mainly in New England because this is something that affected mainly the northern portion of the continent. Canada, the Canadian Maritimes and New England and into New York and New Jersey. But yeah, I never heard of that. Thought I'd just throw it out there.
I never.
I like it.
Yeah.
But let me ask you something, Steve.
Shout it out.
If I wanted to insert a line into this document to denote Cameron's line, how would I go about that?
How would you go about that? You would go to www.formattingformula.com and or YouTube/C/formatting formula for all of your Word document formatting needs. It's so for work the other day, I had to go through 3-hour email training.
What?
Yeah, exactly. Wow. On how to be efficient with your time with email
for 3 hours.
And it's funny because I was like going through this training and I'm like, a lot of this stuff is exactly what the formatting formula teaches you. I mean, don't get me wrong, the training had some use. But the formatting formula is like, you talk about putting lines through things, like how to do a strike through, how to take away a strike through, how to make a list, how to make a bulleted list, how to annotate your list, how to select all, how to, and I know I've talked about this before, this old database where everything's all caps. And the formatting formula taught me how to select it all and then change it all from all caps to all lower caps. Like just all these different little tricks and twists and tips. The formatting formula can really, really just save your butt, save you a ton of time, and more importantly, save you a lot of frustration. I don't know how many times I've tried to embed a figure, or I have 27 figures and I have to add one more, but in the middle, so they teach you how to, so it all populates down, things like that. Anywhere from creating your own privatized headers and ribbons and things like that, all the way down to just, how do I edit my table of contents? So check them out, formattingformula.com or YouTube/C/formatting formula. But more importantly than all of that, make sure you tell them the Geology Flannelcast sent you, because they will hook you up with a 1 to 99% discount. It depends on how they spin the wheel. They have a spinning wheel promotion now. I'm just kidding. No, but seriously, tell them the Geology Flannelcast sent you. And we would really appreciate that. So thanks. Formattingformula.com.
All right. There you have it. Go check them out, ladies and gentlemen. So, all right. So the Taconics are going up in Ordovician into early Silurian time. And
so we're talking 400-ish to 490, 485 to like 440. Right?
Yeah.
Right.
So yeah, they go up, and the other thing that's going on right now is these volcanoes are going off, and volcanoes release some gases, right? And especially when the volcanoes, sometimes if they release enough CO2, it could alter the climate, right? So you'd think that as these volcanoes are releasing carbon dioxide, CO2, it's going to give us greenhouse conditions around this time. But apparently that's not the case. About 10 million years after the uplift, we get an ice age, which potentially, leads to a mass extinction event.
This is one of the, I think this is this the Ordovician extinction event? This is one of the first. This is the first mass extinction.
Oh, in the dude.
So
crack.
It's like you have the Cambrian life explosion, about 540 million years ago. Everything's just like, this is great. And then all of a sudden the Ordovician hits and Mother Nature's like, nope.
Yeah, you got all those sponges and bivalves and brachiopods being like, I'm going to live forever. Nope.
Fame. Anybody?
Yeah.
Old people. I'm going to live forever. Come on.
So the CO2 put out, it's modeled somewhere in the range of like 15 to 20 times modern levels. So it pumped out a lot.
Wow. Yeah. That's a whole lot.
Yeah. So it should be hot.
Yeah. Yeah.
Why isn't it?
Does it have something to do with carbon sequestration?
Yeah, I guess.
Did I just ruin it? Well-oiled machine here.
Yeah.
At the Geology Flannelcast.
Yeah.
I'm sorry. I don't know. Why is it cold?
No. I please answer. Please clap. Yeah. And I think that's something to mention is like whenever anything gets off the surface, nature does not care for it. And it is going to start eroding and weathering instantly. And gravity will do its darndest to break it down. So a lot of times if these rocks are, depending on what they're made of, when they weather, they draw CO2 out of the atmosphere. Right?
So a good question by our Patreon. So if the volcanoes threw out a bunch of CO2, now the planet is absorbing all this CO2. Was it the orogeny that ultimately caused the ice age?
Yes.
Right? That's pretty cool.
Yeah.
Like it's spitting out all this stuff to make it hot, and the planet's like, no. No,
so
we're just
so you get part of this is just natural silicate weather. But in this case, the CO2, it gets into the atmosphere, and CO2 in the atmosphere reacts with water vapor and produces carbonic acid.
Yeah.
Yes.
And so that's why rain is naturally acidic. And so, if you have an acid or a base, neutral is pH of 7. Rainwater is, I want to say like 5.6. It's naturally acidic, just given the CO2 in the atmosphere.
Mm-hmm.
And so with all this CO2, you have a lot of rainwater being produced, but these volcanoes, what were we calling them? The volcanoes.
The volcanoes.
The volcanoes, yes.
Yeah, like it's the Hamptons or something.
Are mainly made of basalt. And so when this acid rain is hitting the basalt, there's calcium in the basalt, and so it's dissolving this out, and it's forming as a runoff. You're dissolving out sort of the calcium, and you're forming calcium carbonate that's in the solution, or will eventually end up in the rock, right? Did I watch that?
Yeah, it's just you're basically getting calcite runoff, right?
Yeah.
It's breaking down. It's turning. Yeah, it's chemically altering the basalts, the lava flows from the volcanoes, and you're getting calcite as a result. So
that calcite's eventually going to deposit when it gets to a body of water where it's super saturated or whatnot.
So yeah, so basically the carbon is getting stored as limestones. Yeah. And so that's what the whole I mentioned carbon sequestration a minute or two ago, and that's kind of like a
mentioned or stole thunder.
No,
I mean, stole thunder. It was I thought it was an alley oop, and I thought it was I thought it was great. Like, why did no. You had this look like you just killed the whole whatever kind of transition you're going.
No, you just took me by surprise. I'm glad. Either way, doesn't matter who makes the basket. We still win the game.
There you go.
The game ain't over yet. We're still in the second quarter, right?
Nope. Let's pack it up and go home.
We're all at the Taconic Orogeny, man. We got the Acadian and Allegheny to go. We got some more ways to go. All right. So what's this about the strontium isotopes here in the limestones?
So this is sort of the way in which they figured this story out. Is they were looking at preserved limestones from this period, and they sort of hypothesized that if they were coming from basalt, they would have a very distinct strontium isotope ratio.
Go Topes.
Which we're not going to get in, because basalt is rich in strontium 86, and so if you're weathering these basalts and it's getting into the waterways and depositing in these limestones, you should have this ratio of strontium isotopes 86 to 87 that has more 86 basically. And is it 80 or is it 85 to 80?
It's 86 and 87.
86 and 87, yeah. So in most sediments the ratio is 0.7, but in these limestones that are deposited at the same time period as this is happening, the ratio is 0.6, which is
huge difference.
The biggest disparity ever recorded.
That's crazy.
Yeah, which is should we so you have all this sediment that's shedding off these mountains, and in this case in the Taconic, most of it is shedding to the west and into the mid-continent, but these limestones are found in modern day Nevada.
What?
Yeah, that's crazy.
We can 86 that idea. For those of you in the restaurant industry.
Really?
Mod. Where's it? Yeah. Cricket sound.
I don't have it.
Let's keep strontium on. So one of the things here, actually, let's just finish this thought before I tie it to the modern. So it was one of the ways in which they sort of, one of the lines of evidence using the strontium proxy to show like that this limestone that you find out in Nevada, and you find actually in the mid-continent, you find all of this sort of Ordovician and Silurian aged limestone in the mid-continent, is likely from the weathered Taconic Mountains.
That's pretty wild that stuff went that far. That's crazy.
So it's drawing CO2 out of the atmosphere, and it draws it down relatively close to sort of modern values, probably about 1,000 parts per million. In the modern day, when we record this,
we're at what, 4 20?
I'm going to tell you, it was last measured yesterday, March 30th. It was 416.8.
416.
Okay.
So we get it down to sort of modern, but probably about 1,800 or 1,000. And at those levels, you might say to yourself, well, that's still really high. Shouldn't it still be really hot? And
Hot tamales.
Yeah. I would say not quite, because the sun wasn't as bright.
The old faint young sun.
Yep. So the sun was just a little bit dimmer. 500 million years ago, it's a few percentages. Let's say it's like 3 or 4% dimmer, which is just enough that at those CO2 levels, it would be cold.
Yeah, that's 3 or 4%. And I'm totally making this number up, but that's the difference between like the dead of summer and the dead of winter.
Mm-hmm.
So just based on how much atmosphere the sun has to go through. So imagine if the whole planet was 3% colder, that's like the dead of winter, which would be Ice Age.
So, you think about modern mountains like the Himalayas or the Himalayas. Depending on your flavor. You get CO2 drawdown just through silicate weathering. You see that, but the level at which you're drawing CO2 down from, say, weathering the Himalayas is not enough. The rate isn't high enough to say send us into an ice age. Because there was some thought when India collides into Eurasia 50 million years ago, 40 million years ago, something like that, 35 million years ago.
Yep.
In that range is right when we collectively, the planet, we go from a greenhouse world to an ice house world.
It's 40 to 50 million years ago.
Yeah. So we get permanent ice sheets that begin to form on Antarctica at like 35, 33 million years ago. And so one of the thoughts was, the uplift of the Himalayas may have driven this. But it's probably not the case. It did probably help or aided the story, but it's not the answer.
Isn't that also when the Laramide was happening as well?
Oh, yeah. Guess so.
So I think it was more than one orogeny going on the planet at the same time.
Probably. And that's you also get the evolution of grass is probably drawing out a lot of CO2.
C4.
But both of the Laramide and the Himalayas, neither of them are basaltic. And so you're not getting the extreme sort of altering the atmosphere, producing this runoff.
Continent to continent.
Yeah, you do have silicate weathering, but it's one of the thoughts is with the taconic, the basaltic nature of it had a pretty drastic effect.
This also ties into episode 50 of the Geology Flannelcast with Chris Conwell.
Oh, yeah.
He was talking about, I was wondering, I was like, why does this sound so familiar? Yeah, Chris is working with the strontium isotopes with this stuff in Nevada. Good friend of the podcast. So Chris talks, if you're interested in this, we got to get moving on with the topics, but so we did talk about specifically, if you're interested in the strontium dating, check out episode 50 with a good friend of the podcast, Chris Conwell.
Yeah, from June of 2020.
Yeah.
So, all right, yeah.
So there you go. So that the Taconic Orogeny kind of more or less affects the northeastern states, New England. That's where the main area of impact was. You really don't see too much with the island arc suturing onto the southern Appalachians. So moving on, you want to what are you guys thinking? Do you want to we'll get with the Acadian Orogeny, but should we make this a 2-part episode, or should we just keep on trucking?
I think we can keep on trucking. What do you think, Jesse?
Let's make our way through the Acadian and then reassess.
Oh, I like it. All right. The Acadian was pretty awesome.
How awesome was it, Steve?
It was so awesome. It happened from 375 million years ago to 323 million years ago. From the Devonian all the way into Jesse's favorite orogeny, or favorite time period, excuse me, the Carboniferous. So 325 would put you approximately right between smack dab in the U.S., between the Mississippian and the Pennsylvanian, correct? Does that sounds right?
Yeah. The break point is 323.2.
Right.
Just off the top of my head. Totally knew that.
But and we have been talking a lot about these time frames and these orogenies, and surprisingly, a lot of these orogenies and time frames line up with the geologic time scale, and some of that has to do with biological evolution either ending or flourishing during these orogenies, because a lot of stuff's happening. We're changing the atmosphere, we're pumping a lot of CO2 in, or we're taking a lot of CO2 out, and we're getting cold or we're getting warm. And a lot of these geologic timescale periods are punctuated by essentially devastation.
Yeah, you don't want to be around at the end of a geologic time period.
I think we are right now, but
it's not historically speaking, it's not it usually doesn't end well.
It's interesting. There is some thought with the Cambrian explosion, which is sort of like one where life radiates, but there is thought that the life that was around prior to that all went extinct.
Well, because of snowball, or what was it? Because of snowball Earth, right?
Snowball Earth, yeah.
And that was like the last thing that was like holding back the explosion of life.
Oh, was it? Well, yeah.
Like the stage was set. Things were getting better on Earth. It wasn't quite your Hadean atmosphere anymore.
Yeah, the Earth was getting all gussied up, just waiting for everyone to show up.
It's got really cold out. I want to do an episode on snowball Earth.
Yeah,
that's coming up. That we need to do that, I think.
I agree.
So back to the Acadian.
Yeah.
We have the collision of the Avalonian, which is where Avalon, New Jersey came from. Continental.
That's not true at all.
What? Continental fragments from the Laurasian continent. So
Avalonia, let me hear your I would like to open this up for discussion to hear everyone's insights on this. Avalonia, exotic terrain or not?
Well, how do you define exotic terrain?
Exactly. That was my like, I don't understand. Like,
because I've heard Avalonia is defined as a microcontinent.
That's the way I was taught.
Yeah,
the microcontinent, and then as far as exotic terrain, like I don't know.
Because I think that's my personal opinion is because we learned East Coast geology. If you learned West Coast geology, you'd call it exotic terrain.
No, I think it's just part of the story, right? Because if that's the case, you can call Taconic age rocks exotic, right? From the island arc.
Yeah, because you're suturing it on, and therefore it becomes new and crazy. It's exotic. So no,
I don't know.
It gets tricky.
I don't know how it just find.
Why call it exotic? Just it's terrain. Come on. It's not that fancy.
Well,
you don't know where Avalonia came from.
Seriously.
Yeah.
Maybe it came crashing in wearing a top hat and a bow tie. It's pretty fancy.
Who knows? Yes. It's not Stone Harbor. Come on.
Nobody outside of New Jersey knows what Stone Harbor is.
Anyway, if there's any New Jersey listeners out there, give us a shout out. Anyway,
besides, nothing's fancier than Wildwood, and I will leave it at that.
Now that we're done,
you find pieces of Avalonia in modern day Great Britain and Ireland, right, and parts of Scandinavia. You find it
Really?
I think so.
I believe you are correct. Yes. Basically,
Wow.
a lot of the, well, I mean, just in general, a lot of the rocks you see in the Appalachians, you see across the pond.
And that's a function of later on in the next orogeny, things collide and then things break up again. They just get carried away.
Yeah. Right now we're still in the collision motif.
There you go. Yeah. But real quick, those are called Wilson cycles, correct?
Yeah, supercontinent cycles.
Yeah. When essentially
200 million year cycles.
My
you come together and you break apart.
Wilson, Canadian geologist.
I didn't realize you were buddies, but now I'm jealous.
He may. Oh no, he died.
God rest his soul.
Yeah. Almost 30 years ago.
Yeah. So Acadian orogeny, we have this, I'm going to call it a microcontinent. I'm actually going to call it exotic terrain. Smashes in, again, northern Appalachia, if you will.
Once again, New England, they just can't. New England and Canada, can't.
Yeah.
New England can't catch a break, It's like they got nailed with the tectonics, and now here comes Avalonia. Boom.
But again, a lot of volcanics, a lot of shed a fine-grained fine-grained clastic material into the inland seaway that covered a large part of the southern and central Appalachia.
Yeah, so you get in the Appalachian Basin, you have these huge, what are called clastic wedges, just these big wedges of sediment, and they're mainly depositing during this time, and there's still some mystery about them. They're oftentimes called deltas because they sort of coarsen upward, which you see in deltas. They're constructional.
Yeah, sort of distributary systems.
Yeah, so the thought is you have like pulses of uplift, what are called tectophases, where you have like this uplift and then it sheds sediment. Who used the phrase buzzsaw before we got on? Erosional buzzsaw.
I think that was me. Yeah.
So you have the uplift, and then whenever you uplift, you're just giving nature sediment to
She hates it.
She does. And so you have these big wedges. And so there's some thought that the Avalonia orogeny is at least three major, it occurs in three major tectophases, three major like uplifts. So there's like this series of the collision is sort of like in these three major phases.
And we're pretty close. We're pretty warm. We're right at the center of the planet, essentially, at this point, correct?
Yeah, we're a little bit south, at least in Pennsylvania, we're a little bit south. But yeah, North America basically straddles the equator till about 30 degrees south.
And you think about it, in the Devonian, we're setting the stage, all this sediment, all this water, we're in warmer climate. You're setting the stage for on land life.
Yeah,
we're giving them that all the ingredients they need to start planting plants.
Yeah, when do we get? Yeah, so we get plants. We get first. We really get our first like land plants during the Ordovician.
That's what I was going to say. The very end, maybe the very end of the Ordovician.
Very end, yeah, late Silurian.
Early Silurian.
Which get those
it's
not Archaeopteryx, it's something really close to that.
Yeah, shoot, blanket on it now.
Yeah.
The fern-like things.
Yeah.
And we get like these little bryophytes first, these little like mossy things. They're all spore bearing. And then is the Devonian when we get our first tetrapods crawling out on the land.
Yeah. I mean, we have a lot of fishes and
Tiktaalik.
Yeah.
The Tiktaalik, whatever. I'm not one for the names, but you get the evolution of basically these tetrapods, these little, like, I don't know how to describe a tetrapod. It's 4 limbs, sort of like a amphibian.
Yeah.
So you need something.
It's like a fish with 4 fins that would kind of swim up and yeah.
There's an interesting story about the evolution of the eyes, and there's some thought about the evolution of the eyes helped these organisms get up onto land because
we talked about this last week.
Yeah, like
2 weeks ago.
2 weeks ago.
Yeah, with our life episode. Yeah.
But you find fossils of these early tetrapods in northern Pennsylvania at this time, like Acadian aged.
Is that the stuff that I know they're at the Philadelphia Academy of Natural Sciences? They have I forget what the name of that thing is.
They think it's Tiktaalik.
Oh, it is that. Okay.
Yeah, that's okay. And you find it Red Hill, Pennsylvania.
Yeah, I was just going to say Red Hill. Yeah.
I've been there once.
Yeah, we all
looked at
rite of passage to get up there.
Is that the Catskill Formation? Question mark. No, what's the red beds there? The red. Aren't there red?
Yeah, I think it's Catskill.
I think Devonian. It is. Yeah, it's Devonian.
If it's red and Devonian, it's Catskill. I'd assume.
You're gonna. Yeah. Some people may disagree with you.
Actually, yeah.
Ugh. Yeah. All right. So, Avalonia rifted from one of my favorite supercontinents, Gondwanaland. I do have a bumper sticker that says "Reunite Gondwanaland." Collided with Baltica in the late Ordovician, and then with Laurentia in the late
Avalonia needs to get itself together.
It sounds like it was like a
bumper car, right?
Pinball, just banging around stuff.
Yeah, I don't know.
Yeah, it's got its like head down, just walking into things.
So, well, listen, gentlemen.
Yeah,
I say we break this up into 2 episodes. We're an hour in.
All right.
Not only do we need to talk about the final phase of mountain building with the Appalachian Mountains, the Acadian Orogeny, we also need to talk about how they got to the point where they're at today.
That's a good point.
So,
I thought Jesse summed that up in the first sentence.
The mountains go up, and the mountains
come down.
It's the end. The circle of life right there.
I guess we're still in the mountains go up part.
We're still, the mountains go up, the mountains go down, the mountains go up, the mountains go down. We're in the mountains go down part right now. Because,
wait, does this mean I don't have to pick a topic for next week? I'm in.
Yeah, you saved yourself 1 week there, my friend. But so I guess to finish things off, we can end it with this thought here. The mountains that we're talking about, like we talked about the Taconics, the Taconic Orogeny, and then the Acadian Orogeny, we don't have those mountains aren't around anymore. So it's, how do we know that they were there? And one of the ways, there's actually a couple different ways that you can tell that the mountains were coming in.
Ghost mountains, like the ghost ships that we just got them talking about. Now you can see basically as soon as they go up, Mother Nature starts tearing them apart, and we see the giant pile of sediment that Mother Nature left behind after she started tearing these mountains apart. So we see that with the Taconics and
the Acadian Mountains. We basically like,
and even the Grenville.
Yeah. Well, the Grenville, we can actually, we can bring Grenville back for the Allegheny orogeny, because that's when Grenville starts to poke its ugly, well, I don't know about ugly head, but the Allegheny orogeny kind of brings some of that Grenville stuff back.
Yeah. Hey guys, remember me?
Yeah. But we talk about these things like clastic wedges, and you get this giant pile of sediment from where the mountain used to be. And we're going to talk about this next week. Like if you look at like the East Coast of the United States, you have like the Appalachian Mountains kind of hugging, offset from the coast just a tad. But then you go directly east of the Appalachians and you get the Piedmont, which is all the metamorphic rock, the really old like billion-year-old metamorphic rock just east of the Appalachians. But then after you get through the Piedmont, it's pretty much just coastal plain from going up to just about all of the East Coast, from Florida all the way up to New England. And
it's going to be more of Steve just naming New Jersey beach towns.
Yeah, how New Jersey, and but he can actually legitimately say how these New Jersey beach towns came about for next week. But no, it's just a giant.
Let's talk about Seaside Heights.
It's just a giant pile of sand. All the coastal plain is just a giant pile of sand that's left behind from the once mighty Appalachians that have since been just totally denuded. You like that word?
Denuded.
Yes. Totally eroded down to where they're at today. So I say we leave it at that, ladies and gentlemen.
Yeah, well, but seriously, thank you very much to our Patreon. Some of them gave us some excellent points to talk on today. So thank you. And if you're ever interested in becoming a Patreon, please check us out. Patreon.com/Geology Flannelcast. Blah, 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 doobie, doobie, doobie.
Spell all that out.
Exactly. No spaces. And check us out on Twitter, Facebook, Instagram. I don't know what else.
Twitter, Facebook, Instagram. That's that's it.
Yeah.
Kelly
Blake actually posted our latest Women in Geology Flannelcast on LinkedIn. So even if you're on LinkedIn, check it out.
Yeah.
Give us a like, give us a comment.
You want to connect with the Wing group, Women in Geothermal. Whatever, catch them on LinkedIn. Yeah.
And also, if another way to help out the podcast, I know we talked about the Patreon website. We have patreon.com/Geology Flannelcast. If you go to geologyflannelcast.com, if you don't want to do a subscription, you can help us out by just picking up some merch. So we got some stickers, very reasonably priced stickers on the website there. The lovely Geology Flannelcast coffee mug, if you're interested in that.
Oh, and it really does make your coffee taste 20% better.
My goodness, my coffee was so delicious this morning.
At least I ate ice cream out of mine the other night.
I'm not gonna lie, I can't drink coffee out of anything but that mug now. It just doesn't taste good.
4.6 billion years in the making. Also, you get some t-shirts. So anyways, all this fun Geology Flannelcast merch on there if you'd like to help out the podcast that way. Or just tell a friend. Hook us up and tell a friend. That helps out a lot too. So that being said, thank you so much, everyone. And come back next week for the second half of the Appalachian Mountains. And I mean, things are gonna get real in the next episode. It's good. You want to talk about collision. Woo! We're gonna have some collisions for you guys.
You probably don't know how this is gonna end. Get ready.
No, spoiler alert: they go up and they come down.
They're gonna come down. So.
Sorry.
All right,
you got to learn how they come down.
Oh, I got nothing. Anyway, all right. Thank you for listening. I really appreciate it, Chris.
How about a little throwback before we end? Jesse, what song are you taking us out with today?
Oh boy.
he was not expecting this.
All right. How about
I wasn't expecting
why
this.
do you build me up, Buttercup?
That's the first thing that came to mind too. Yeah.
We hadn't done that in about 5 years.
No.
Yeah.
Build me up, Buttercup.
All right, everyone. We'll see you guys next week. Bye.
Bye.